Hi, today I'm going to show you, uh, or rather explain, how does a projection of a Gaussian splat happens. So, what exactly is a Gaussian splat? So, a Gaussian splat is, which is in 2D, is basically there are something called as point clouds, which is generated. These point clouds are in fact generated through through an algorithm called an SFM, which you can do it with a software called CallMap. Now, now in Gaussian splatting, what people do is this is in 3D. They take each of these points, point cloud or sparse cloud, and and place a Gaussian on it. So you place Gaussians, 3D Gaussians. It's like a sphere, 3D Gaussians. You put a spherical 3D Gaussian. I mean, Gaussians are not a sphere, it can vary. Uh, and each of these Gaussians, right, each of these Gaussians is influenced by the mean, which defines the position, then the covariance, which determines the shape and orientation. We will, in the next video, we will kind of decompose this covariance into rotation and scaling. So, because optimizing this is not that straightforward. Then we have the color, which changes based on the viewing direction, changes based on the viewing direction, uses something known as spherical harmonics. I'll put it as such. And finally, opacity, uh, alpha. This basically shows how much of a solid it is. How much of a solid, as in how much solid it can be. I mean, if it's transparent, it's not too much of a solid, it's a light solid. And if it's high alpha, that means a hard solid. So, so with these parameters, we can actually build a Gaussian. Now, based on these values, we can generate different shapes of Gaussians. And mostly Gaussians are ellipsoids. So how do you know which is the perfect one? So this, right now, a spherical one is an isotropic Gaussian. These ones are non-isotropic Gaussians. Now, uh, why do we need a non-isotropic Gaussian? Suppose there's a 3D scene of a grass or a tree. Using isotropic Gaussians, it's very difficult to represent it because we need to use a lot of spheres. This is very, this is not good at all. So what we do is we take this, we elongate it, then stretch it. Like we can do a lot of weird operations. So we can essentially represent grasses, right? So the nature of a Gaussian actually helps us to do this. 3D Gaussian helps us to represent interesting shapes and sizes. Now, how do now how do I know these parameters for a grass? You actually have to learn it. So these all are learnable parameters. I mean, you don't use deep learning. The learning works in a different way. It uses something called it uses a stochastic gradient descent, and it uses this and compares these values with the training image. Training images are just the pictures that is taken around the scene. Now, let's talk about the agenda of the video. The agenda of the video is, now I know I have point clouds. I have determined the Gaussians, and I have determined the non-isotropic Gaussians as well. Now this is a 3D Gaussian. How to represent in 2D? Because how to represent it in an image, right? Because uh, because the screen is essentially 2D. How do we represent this in x comma y? So point can be represented easily because point is mu, right? The mean, and the shape and size is determined by the covariance, which is sigma. So essentially, we have a Gaussian distribution function. Sorry, we have a Gaussian function, let's say g of x, and that is determined by e to the power minus 1 by 2 x minus mu transpose sigma inverse x minus mu. Now, I need to project this to 2D. So Gaussian of 2D of x should be e of minus 1 by 2 x minus mu dash, which is in 2D, and a sigma dash of inverse x minus mu dash. So how do you estimate these two from these? Uh, Representing mu is easy because mu is determined by x, y, and z. This is the world space. Now I need to get mu with the perspective of the camera, right? Suppose this is me. I'm viewing this, and there's a point here. Viewing the point here and here is different, right? Like these points are different. So I need to get it into the perspective of the camera because we are taking multiple pictures from each camera, and we take the the perspective of that object from multiple angles, and what are the Gaussians and what are the Gaussians in that local perspective. Like I'm observing the Gaussian from that local perspective, right? I have a local perspective and I'm observing the Gaussian from that local perspective, and I want to see how does my Gaussian look, because I'm generating a 3D scene in a computer which is 2D. Because so that's why using perspective projections in the first place, right? So first, what we do is we take mu, yep, and we project it to the camera's perspective, right? For that, we use something called as an extrinsic matrix. So so if I take mu, let mu dash be the point of the mean from a camera's local coordinate. So that is determined by multiplying it by the extrinsic matrix of the camera, which contains the camera's pose and some details. Multiply that with mu. So this gives uh, so this gives the camera's the perspective of the Gaussian, like the location of the Gaussian with respect to the camera, a local camera, and and then now we need to project it to a 2D scene. So for that we use something called as perspective projections. So that is basically f of x multiplied by x dash of z dash plus uh, there's a principal point. There's something known as a principal point for a camera, which you get from an intrinsic matrix, I think. Yeah. So do the same thing with the help of the intrinsic parameters. We can find the other point. So u dash. So this gives us an x comma y basically. So this is how we project it in 2D. So x dash is f of x dot c of x, and y dash is, I'm not going much into the details of perspective projections because this is straightforward formula. It basically follows the pinhole project perspective. Suppose there's a tree, there's a man or whatever. A is in 3D space. There's a pinhole, and there's an image plane, right? So how do I get this guy in the image plane? So you go through the pinhole camera, and then yeah, get this man in inverted way. This is focal length. There are some principal points x and y. So this point u comma v is determined by s f of x and 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 it's sorry x of z. So same by v is like this, f of y, and y divided by z of z. This is with the help of a similar triangle similarity formula. Yeah, triangle similarity. This uses a triangle similarity. So from this, you can find u and v, which is this. So, finding the point is fairly straightforward with perspective projections, which uses triangle similarities. But now doing that, now how do I do that for something like, how do I do that for covariance? So covariance, it's not that easy because first covariance, what we do is we multiply the covariance. We need to find this, right? So we need to find a sigma dash first. So that we can do by multiplying by the uh, extrinsic matrix. Now we need to find this. Now, uh, now doing a perspective projection of the covariance in the local coordinate system of the camera is not possible. This is perspective projection. This is a symbol of perspective projection, by the way. It's not that straightforward because division by z makes the perspective projection non-linear, and applying a non-linear transformation in a Gaussian distribution or Gaussian can not lead it to be a Gaussian, maybe, is what I read, and doing that can make the view very weird. It will make it look in a very weird way. So that's not something needed. That's not good. So what they do is they take the uh, Taylor expansion of the perspective projections. So that gives a Jacobian matrix, and it's basically the differential of it's basically the differential or the Taylor expansion of the perspective projection. You differentiate the perspective projection. So and that you multiply with the sigma. So we take this. Yeah. So now we take the Jacobian of this, and this will give us a 3 cross 3 covariance. This is basically in 2D, so we get rid of the third row and last column. So we get a, a 2 cross 2 matrix. So this is so yeah, this is how you get the shape of a 3D Gaussian to 2D image space. So the key is you don't directly project it with the perspective projection, but rather uh, you need to take a differential of its perspective projection. So we take a Jacobian of the perspective projection. So that's what it is. So it's so in the paper of the Gaussian splatting, they say you take a Jacobian of the projection with respect to the camera view. So that's basically perspective projection because you are converting the 3D object into 2D with perspective to the camera. So yeah, that's it. So this is how this is. And in the next video, I will show you how you can optimize Sigma. Because Sigma, we need to optimize it in a certain way that uh, Sigma should be Sigma should fix should get to the shape of the covariance should when the Gaussian 2D Gaussian should come into the shape of the 3D object. So we need to optimize sigma. So we can't so the key is that we can't directly optimize sigma. So we can't directly optimize sigma because because the stochastic gradient descent can give negative values to sigma, which is not good. So we do a decomposition of sigma, which is represented by scales and rotations. And we take these rotations and scaling this rotation is a quarter is in quaternion space. I don't know, I was spelling, but, and this is the scale. So you take a diagonal matrix with s of x, s of y, and s of z. So we optimize this separately. So that's we will discuss in the next video. So thank you.